This lecture is on the Lorentz force. Now before we go into the Lorentz force, it's useful to go over right-hand rule. This right-hand rule is sometimes called right-hand rule number 1, and right-hand rule number 2 we'll go into in the next lecture when we talk about Ampere's law and the magnetic field created by a current. When we have two vectors A and B, there's something called a cross product of the vectors A and B. The cross product of two vectors is itself a vector, and so it also has a direction. Right-hand rule number 1 tells us the direction. Given the directions of A and B, it tells us what the direction of their cross product C is. We'll look at the magnitude of C in a little bit, but first we're going to talk about the direction of C, and that's what the right-hand rule gives us. It'll be helpful to start with some 3D axes. Okay, so this is a horizontal and this is a vertical, and this, I've drawn it, I mean for this to sort of be coming toward you, toward the viewer. So you can almost think of these three axes as being like what you would see if you look into the corner of a room. Okay, so here's the floor, and here's one wall, and here's another wall. Anyway, so horizontal, vertical, and kind of toward you. Now let's suppose that the two vectors A and B are pointing as drawn here. So A is pointing to the left and B is pointing toward us. The right-hand rule is going to tell us the direction of C. So here's how it does that. If I take my right hand and I point my fingers in the direction of B, sorry, in the direction of A, not in the direction of B, so I start my fingers off pointing in the direction of A, and then I sweep my fingers, partially closing my hand, so that my fingers now point in the direction of B, then the direction of my thumb tells me the direction of the cross product A cross B. So in this case, the cross product A cross B is pointing up because that's the direction my thumb is pointing. So to go back to our original drawing with 3D axes, it's pointing up. So once again, start off with your fingers pointed in the direction of A. Close your hand partially, sweeping your fingers in the direction of B, and then wherever your thumb had to point in order for you to be able to do that, in order to sweep your fingers from A and towards B, whatever direction your thumb had to point, that's the direction of A cross B. Note that the cross product of two vectors is always perpendicular to both of those vectors. A and B need not be perpendicular to each other. So here I'm trying to draw B instead of at a right angle to A, pretty close to A. So the angle between them is relatively small. You can still sweep your fingers from A to B, and as you do that, your thumb will have to be pointing up, and that's the direction of the cross product. And the cross product is still perpendicular to A and perpendicular to B. So that covers the direction of C. What about the magnitude of C? The magnitude of C, or the magnitude of the cross product of the vectors of A and B, because that's what C is, it's equal to the magnitude of A times the magnitude of B times the sine of the angle between them. So theta is the angle between A and B. So in this drawing over here, the angle between A and B are drawn perpendicular. So theta is a right angle, 90 degrees. Similarly in this drawing, it's a right angle, 90 degrees. In this drawing down here, however, theta is smaller than 90 degrees. It's useful to note that the cross product for theta equals 90 degrees, as in these first two pictures, the sine of theta is 1. So the cross product is just the magnitude of A times the magnitude of B in that case. Where theta is less, sine of theta is less, so the cross product is less in this case here. If theta is 0, that is A and B are parallel, then sine of theta is 0, and that means that the cross product is 0. So, parallel vectors, the cross product of parallel vectors is always 0. And that's kind of good, because the right-hand rule wouldn't give us a clear result in the case where the vectors are parallel. How would you sweep your fingers from A to B if A and B are pointing in exactly the same direction? So the right-hand rule can't really give a result for parallel vectors, but that's fine. The vector is just the zero vector in the case of the cross product of two parallel vectors. Okay, now that we know how to deal with a cross product using the right-hand rule, and the rule that the magnitude of the cross product is equal to the magnitude of the two vectors times the sine of the angle between them, now we're in a position to understand the Lorentz force. If you have a magnetic field, the magnetic field exerts a force on any moving electric charge. The Lorentz force tells us what that force is. It says that the magnetic force, F sub B, is equal to QV cross B. Okay? Q is the charge of some particle immersed in the magnetic field, V is the velocity of that particle, and B is the strength of the magnetic field. Note that both velocity and V are vectors. There's a cross product, and so we can find out the direction of the force using the right-hand rule. So to aid in 3D visualization, here are our axes. It's like the corner of a room. Maybe this room has a comfy sofa and a bookshelf with books. Let's consider a positively charged particle moving to the right through the room. It's got some velocity v, and it's moving right through a uniform downward magnetic field, B. What then would be the direction of the magnetic force on the particle? Well, V cross B. Using the right-hand rule, I point my fingers to the right in direction of V, and then I close my hand partially to sweep my fingers downward, because that's the direction of B. And if my fingers start pointing to the right, and then I close my hand partially to point them downward, that means my thumb must be pointing into the page or away from us. Remember that force is perpendicular to both the direction of travel and the magnetic field. So this is going to cause the particle to curve to the left, and the magnetic force is going to continue to be perpendicular to the changed trajectory of the particle. So as the particle curves left, the magnetic field rotates to the left with the change in the direction of the particle's direction of travel. Because the force is always perpendicular to the direction of travel, this means that the velocity of the particle never changes. So as it changes its direction, its speed, or the magnitude, I should say, the magnitude of the velocity never changes, the speed never changes. As the direction of the velocity changes, but the speed changes the same, and we have a constant acceleration perpendicular to the direction of travel, well, this is a description of uniform circular motion. So I've done my best to draw a circle. It's parallel to the floor. Okay, that's what I'm trying to draw here. A circle that's parallel to the floor, and the particle is just going to go around in this circular path. And at every point on this circular path, the magnetic force is pointing perpendicular to the circular path, and it's never changing in magnitude. Okay, that's because the magnetic field, I said earlier, is uniform. The velocity is not changing because the force is perpendicular to the velocity. Sorry, once again, it's the speed that doesn't change, or the magnitude of velocity that doesn't change. The direction of velocity is changing. So the magnetic force is perpendicular to the path, the trajectory, and it is unchanging in magnitude. So this means that it is a centripetal force. It's the centripetal force that's keeping this particle moving in a circular path. One thing I want to note about this example is that if the charge had been a negative charge, then the force becomes a negative of what you get from this cross product. In other words, it points in the opposite direction. So in that case, the particle would have curved the other way, like so. Now I want to quickly define the notation for vectors pointing into and out of the page. Vectors can of course point up, down, left, or right. We can also consider a vector going into the page, or into your screen, I guess, and that is denoted by a circle with a little X in the middle. A circle with a little dot in the middle denotes a vector coming out of the page, toward you. So, directly away from you, directly toward you. These are understood as being exactly perpendicular to the page. So we'll use this notation for our first homework problems. For these 4 cases of a particle with some velocity v moving in a magnetic field, determine the direction of the magnetic force on the particle. Note that in 2 of the cases, the charge of the particle is negative, and so that means that the magnetic field is going to, the magnetic force is going to be opposite the direction of what the right-hand rule gives you. So for each of these 4 cases, give the direction of the magnetic force. Let's talk about the units of magnetic field, and let's consider, with Lorentz law, the case where the velocity is perpendicular to the magnetic field, so that the angle between them is 90 degrees, sine of 90 degrees is just 1, and so if we're just talking about magnitudes, we can think of this as simple multiplication. Solving for b, we get that it is F over qv, so this is some number of newtons per coulomb meter per second. A newton is a kilogram meter per second squared, and we find that that reduces down to kilograms per coulomb second. That's a mouthful, so there's a short name for it. The short name for this unit, kilograms per coulomb second, is the Tesla, or T, abbreviated as T. So the Tesla are the fundamental standard international units of magnetic field. Let's do a sample problem. A particle is accelerated through a 1-volt magnetic field. Note 1-volt electric potential. 1-volt electric potential. There's no such thing as a 1-volt magnetic field. That doesn't make sense. That was a mistake. A particle is accelerated through a 1-volt electric potential. It's accelerated horizontally and immersed in a uniform downward 10 to the minus 4 Tesla magnetic field. It curves left following a circular trajectory with radius 4.18 meters. What is its charge to mass ratio? Charge to mass ratio means Q over m. Well, we can use the Newton's second law because we know something about the force, it's the magnetic force, and we know something about the acceleration, it's the centripetal acceleration. The magnetic force is just QVB. The sine theta isn't there because in this case the angle is 90 degrees because the velocity is horizontal and the magnetic field is downward. So sine of 90 degrees is 1, the sine of theta just disappears, leaving QVB for the force. And the centripetal acceleration is v squared over r. The v on the left side cancels with one of the v's on the right side, so this simplifies to QB equals mv over r. Using the fact that this particle was accelerated through a 1-volt electric potential, we can equate the electric potential energy it gains with its kinetic energy. This is an application of conservation of energy. We've assumed here that the particle started from rest. Now I'm solving for v squared, and the reason that we do that is because v is in here, and v is a nuisance variable. We neither know it, nor is it something that we're trying to solve for, so we should just eliminate it by using this equation. Now, because this is an expression for v squared, rather than dealing with a square root, what I'm going to do is I'm just going to square both sides of this equation. Now I can substitute in this expression for v squared right here. The m on the bottom here cancels one of the m's on top, and this q on the right side cancels one of the q's on the left side, leaving us with this, and we can now move the m over to the bottom of the left side and the b squared to the bottom of the right side, and then we will have solved for q over m. Wonderful. Everything's already in standard international units. The radius is in meters, the b I gave in Tesla, and the voltage I gave in volts. So there's no unit conversions that need to be done. We can plug in numbers. I found 1.1 times 10 to the 7, and that's in coulombs per kilogram. Note that this particle curved left as it moved through a downward magnetic field. That is in accordance with what we found earlier here for a positively charged particle. So that means that this particle is positively charged. For homework number 5, answer the same question as the previous example problem, but this time with the particle curving to the right with a radius of 3.38 centimeters. Find this particle's charge to mass ratio. Be sure to note whether the charge is positive or negative. One final thing I'd like to note about the Lorentz force is its QV cross B. But if we consider a wire with some current moving through it, the current is the charge divided by the time it takes to move through the wire at some velocity, where the velocity would then be the length of the wire divided by the time. Distance over time. Q is then equal to I times delta T. QV is then I delta TV. Replacing V with L over delta T, we get that QV is IL. Of course, this just cancels. We can rewrite the Lorentz force then as Li cross B, where I is considered to be a vector pointing in the direction of the current flow. So, just as there's a Lorentz force exerted on a moving charged particle, there's also a Lorentz force exerted on a wire carrying some current that is immersed in a magnetic field. And that Lorentz force is given by the length of the wire, the current through the wire, and the magnetic field.